Today we're going to be discussing related rates. So this is a calculus problem that involves related issues in various applications of mathematics and physics. For example, if we're pumping air into a balloon, both the volume and radius are changing over time. Though their rates of increase are not the same, they are related. We can use one of the rates to calculate the other rate. In related rate problems, we begin by finding an equation that relates the two or more variables and then differentiate using the chain rule. So for instance, if we wanted to make this one really simple, let's suppose that the balloon is a perfect sphere. Now, we know that the volume of a sphere is equal to 4/3 times pi times the cube of the radius. So the volume and the radius are directly related. As the radius increases, the volume increases. As the radius decreases, the volume decreases. So the question is, how does the change in radius affect the change in volume? Let's start with an example. So air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius changing when the diameter is 50 centimeters? So what we do know is we know that the volume is changing over time, and we know what that rate is. In other words, we know that the change in volume, the differential of volume with respect to time is 100 centimeters cubed per second. What we want to know is the rate of change of the radius with respect to time. Now, we can relate those two with a missing rate, dV dr, the change in volume with respect to the change in radius. When we went over the chain rule, we kind of covered this. We know that the derivative of the volume equation with respect to time is equal to the derivative of the volume equation with respect to the radius times the derivative of the radius with respect to time. So what we don't know is this one. What we do know is this one. What we need to find in order to find that unknown is this one, which we can do using our equation, the equation I just gave you. Volume equals 4/3 pi times the radius cubed. So taking a simple derivative here, we don't even really have to use the chain rule with this one. We can stick with basic differentiation. We get 4 pi r squared. So, back to our formula. Back to this right here. dV dt, which we know is 100, is equal to dV dr, which we know is 4 pi r squared, times dr dt, which we're trying to find. So it's pretty easy to solve for that now. We simply divide both sides by 4 pi r squared. And we get 25 over, started to write pi there, over pi r squared. Now, if we go back to the question, it asks us, how fast is the radius changing when the diameter is 50 centimeters? So notice what we have in our equation here. The rate of change of the radius is subject to the current radius. So if we're talking about the diameter is 50 centimeters, then obviously the radius is 25 centimeters. So we plug that in. dr dt equals 25 over pi times 25 squared, which is equal to 1 over 25 pi, and our rate would be centimeters per second. So every second, the radius is increasing. I should say it this way. At the time when the radius is 25 centimeters, the radius is increasing at a rate of 1 divided by 25 pi, or approximately 0.0127 centimeters per second. So if we took an estimate at a different time, if we looked at when the radius was 10 centimeters or when the radius was 100 centimeters, that change in radius would be different because it's related to the current radius and the current volume. Let's consider a similar problem. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So I find it helpful, especially in situations like this, to draw a picture, which is rough because I'm not very good at drawing pictures. So let's suppose we've got the wall, the ground, and our ladder. Now this ladder is 10 feet long. We've got the height that it reaches on the wall, which we're going to call y, and the distance from the wall to the bottom of the ladder, which we're going to call x. Now, here's what we know. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. Okay. So, dx dt is increasing by 1 foot per second. Okay. The x value is changing at a rate of 1 foot per second. Okay. And the current time that we're going to talk about is when the bottom of the ladder is 6 feet from the wall. So we're going to be looking at when x equals 6. So here's some other things that might be helpful. We want an equation that relates x and y. And we can use a simple Pythagorean theorem. X squared plus y squared equals 10 squared, or 100. Okay. So let's start by taking the derivative of each side. We're going to use implicit differentiation and the chain rule here. And the reason we're applying the chain rule is because we're taking derivatives with respect to t rather than derivatives with respect to x or y. So when we take the derivative on each side, the derivative of x squared is 2x, and we've got to throw in a dx dt. The derivative of y squared is 2y. We've got to throw in a dy dt. And the derivative of 100 is 0. Okay. Now, if we want to solve this for dy dt, and the reason we want to solve this for dy dt is because we're looking at how fast is the top of the ladder sliding down. We're talking about a change in the y value. So if we'd solve for dy dt, we get negative 2x over 2y and a dx dt, okay, which we could reduce to negative x over y dx dt. Now, we know a couple of things here. We know this value because it tells us that the bottom of the ladder is sliding away from the wall at a rate of 1 foot per second. We also know x because we're talking about when the bottom of the ladder is 6 feet away from the wall. What we don't know is y. Okay? However, we can use our original equation to find y. So I'm going to take some of this information over to the next page. All right, let's fill in what we know. Okay. dy dt equals -6 over y times 1. So let's solve for that y. We're going to use our Pythagorean theorem equation. We said x is 6 at this moment. We don't know y, but simple algebra tells us that y is either plus or minus 8. Now, obviously, we don't care about the -8 because that would mean that the top of the ladder was 8 feet below ground. Not what we're going to consider in this case. So, we're going to use 8 feet. So when we put that in, we get dy dt equals -6 over 8 times 1, which is -3/4 feet per second. So what that tells us is, going back to the question, reinterpreting it in terms of the question that was asked, when the bottom of the ladder is sliding away from the wall at a rate of 1 foot per second, the top of the ladder is sliding down the wall at a rate of -3/4 feet per second. Interpret that any way you want. It's dropping down the wall at 3/4 of a foot every second, or it's dropping down the wall 3 feet every 4 seconds, but that's going to change when x changes. Okay? Everything is subject to where it is at the time. Okay? If you actually watch this in motion, you would see that the ladder picks up speed or slows down at various points. Okay? So it's all subject to exactly where the ladder is at that time. All right, that's where we're going to stop for now. I'll make another video with a couple more examples, so keep a lookout for part 2.